You know that an electrochemical cell or a galvanic cell can be constructed with any two given electrodes. The two electrodes would form the two half cells. One would be acting as the anode, other one would be acting as the cathode. Now in the picture here, you see a voltaic cell constructed with zinc and copper electrodes. There is a specific way in which this cell is represented, which is called the galvanic cell representation. I will show you how. Here zinc is the anode. So first we will write the anode metal on the left and then draw a vertical line. Write the electrolyte that is in the anode compartment. It is zinc sulfate here. Zinc sulfate. We have to represent the concentration of the solution. Since the conditions are standard, the concentration is 1 molar. Then we have to draw two vertical lines to represent a salt bridge. Here on this side, you have to write the electrolyte in the cathode compartment, copper sulfate. Here also we will write it as aqueous. Aqueous. Concentration 1 molar. Draw a vertical line and the copper cathode or the cathode metal. There is another way of writing it, that is you write zinc and then instead of mentioning the salt completely, you can show the zinc ions. Zn2 plus aqueous 1 molar, salt bridge Cu2 plus aqueous 1 molar, a vertical line and Cu solid. So this gives a complete representation of the galvanic cell without the diagram. Once you do this, it will be easy to write the equation for the electrode reaction. That will be the next thing. How to write the chemical reaction, that is the based on which the cell is constructed. Anode metal becomes the ion. So zinc solid becomes Zn2 plus ion. Aqueous. See here, the metal forms the ion. So the metal is the reactant, ion is the product. So metal we are writing on the reactant side, ion we are writing on the product side. On the right hand side, the ion that is in the cathode, the ion becomes the metal. So ion is the reactant and metal is the product. So we will write here Cu2 plus aqueous and write copper solid as the product here. So this is how you write. The anode metal becomes ion, the cathode ion, anode metal becomes ion, cathode ion becomes the metal. So this gives you the galvanic cell representation and also the equation for the cell reaction. Let's have one more example. I am giving you the equation for the cell reaction here. Mg solid with 2 Ag plus aqueous giving Mg2 plus aqueous plus 2 Ag solid. Using this equation, how to write the galvanic cell representation. Now from this we know that magnesium is the anode because magnesium is forming the ions. So that is the anode. So we write the anode metal on the left side. Mg solid, vertical line, Mg2 plus aqueous 1 molar, salt bridge, cathode ion is Ag plus aqueous 1 molar, Ag solid. When you are given zinc and hydrogen electrodes, when you have to set up a cell with zinc and hydrogen electrodes, let us practice representing the cell. You know, in that combination, zinc electrode and hydrogen electrode, zinc is the anode. So it will be Zn solid, Zn2 plus aqueous 1 molar, H plus aqueous 1 molar bar, H2 gas. Here you have to involve the platinum metal which is providing the electrical contact. For all the gaseous electrodes, you have to write the metal. Normally it would be the platinum electrode, the inert electrode, which will be giving the electrical connection when used as for the connection. So you have to represent the metal also at the end. How to write the equation here? Zn solid plus 2H plus aqueous giving Zn2 plus aqueous plus H2 gas. Once the cell is constructed, we must know what is the EMF of the cell. That is given by E0 cell is equal to E0 of the cathode minus E0 of the anode. The electrode potentials of different metals are tabulated. From that we can take the standard electrode potential of the two metals that are used for setting up the cell, and once we write the representation, cell representation, we know which is forming the anode and cathode, and we can calculate this E0 cell. For the voltaic cell involving the zinc copper electrodes, it will be E0 Cu2 plus bar Cu minus E0 Zn2 plus bar Zn. These values are 0.34 volt minus 0.76 volt, and you get a value of 1.10 volt. Supposing I give you a pair of electrodes and ask you to construct an electrochemical cell and calculate the E0 cell. What would be the first thing that you have to do? You have to select the anode and the cathode out of it. For that you will have to look into the list of the standard potentials. The one element for which the electrode potential value is lower would be forming the anode. Remember, it is the list gives you the list gives you the values of reduction electrode potentials. So the one having a lower value is readily oxidized. Hence, that should be taken as the anode, and the element for which the electrode potential is higher will form the cathode. Once you know the anode and the cathode, you can write the galvanic cell representation, which would enable you to calculate the E0 cell. The first question is, represent a galvanic cell. Represent a galvanic cell using chromium and silver electrodes. Using chromium and silver electrodes. Write equation for the cell reaction. Equation for cell reaction. Calculate E0 cell. Calculate E0 cell. So what is the first thing that we have to do? We have to look into the list for the E0 values. Chromium is not given here. The list we don't find chromium. The value of E0 Cr 3 plus bar Cr is minus 0.74 volt. Silver you find here, that is 0. This is silver. Looking at the values, now you know which one should be the anode. So let us write the representation. So we will have chromium as the anode, Crs line, Cr 3 plus aqueous 1 molar, salt bridge Ag plus aqueous, Ag solid, 1 molar. Have you written the equation? Equation is Cr solid plus Ag plus aqueous. Anode metal, cathode ion, giving anode ion and cathode metal. To balance the charges, we write here. Now E0 cell would be E0 cathode, which is cathode here, Ag plus bar Ag, minus E0 Cr3 plus bar Cr. So that gives you a value of 1.54 volt. The second problem. Arrange K plus bar K, Sn2 plus bar Sn, Ag plus bar Ag and Fe2 plus bar Fe in the increasing order of the reducing power. Increasing order of the reducing power. The values of the standard potentials of these elements are given. Look at those values. We have already seen that the one with a lower value for the standard potential would have greater reducing power. In other words, the one which has a lower reduction electrode potential. We know the standard potentials are the standard reduction electrode potentials. So the one with lower electrode potential or lower reduction electrode potential will be oxidized spontaneously. So when it is oxidized spontaneously, it would be a very good reducing agent. Hence, the one with the lowest value will be having the highest reducing power. The one with the highest standard electrode potential value will have the least reducing power. That way, we find that silver has the highest value here. So Ag plus bar Ag will be having the least reducing power. We are arranging in the increasing order. So first we have to write the one with the lowest reducing power. Then comes your this is minus, I'm sorry, this is minus. So then comes your tin which is minus 0.14. Then you have Fe 2 plus bar Fe with minus 0.44, and the last is K plus bar K, which should be the best reducing agent. So this is the way you have to arrange. Remember one thing, when you are arranging in the increasing order, the sign that you have to write is less than. I have often seen students writing the correct order, but they put the wrong symbol here, they put greater than. Or the best thing would be put a comma. So this is the order in which the metals are to be arranged in the increasing order of the reducing power. If it is oxidizing power also, you can think accordingly and write the answer. The third question is, can you stir a silver nitrate solution with a copper spoon? You are given the E0 values of the silver and copper electrodes. In this case, do you want a reaction to take place? No. So, if we don't want a reaction, we should check up whether these two electrodes, a silver copper spoon or a copper metal, can form an electrochemical cell with silver nitrate solution. There are a few ways in which you can look at the working out. That is, here copper is in the metallic form. So the reaction would be copper solid. Copper should form the anode. Copper solid should reduce the silver ion. Should reduce the silver ion to form copper ion and metallic silver. If this reaction could take place spontaneously, then a cell would be set up. The cell would be like this. It will be Cu solid bar Cu2 plus aqueous and then Ag plus aqueous bar Ag solid. Let us calculate the E0 cell of this. That is E0 cathode, which is cathode here silver. So E0 of Ag plus bar Ag minus E0 of Cu2 plus bar Cu. The values being 0.80 volt minus 0.34 volt, it is positive. Since the E0 cell value is positive, we are sure that an electrochemical cell would be set up between the copper metal and silver nitrate, and this reaction would be spontaneously taking place. That means there will be reaction and we cannot use. So the answer here is no. The next question is a similar one. Can you store magnesium sulfate in copper vessel? Let us see. Can you store magnesium sulfate in copper vessel? Will you be able to do it? Let me give you the values of E0 Mg2 plus bar Mg, which is minus 2.37 volt, and by now I think you all remember your electrode potential of copper. It is 0.34 volt. Again, we should see if an electrochemical cell would be set up between the two. Here copper is in the metallic form and magnesium is in the ionic form. Let us approach it in a different way. Let us write the equation Cu solid, isn't it? This is in the metallic form. So if at all a cell is set up, that would be forming the anode, and magnesium is in the ionic form, so that should form the cathode. Cu2 plus aqueous plus Mg solid. Look at the values. Here magnesium has a lower value. So magnesium has higher reducing power than copper. But as per the equation, copper should reduce the magnesium ions, which is not possible. With magnesium having lower value for electrode potential, copper having higher, copper will not be able to reduce the magnesium ion. So directly looking at the values, we can say no reaction will be taking place. No reaction. Hence, we can store. So looking at the values, you can give your argument based on the values, or you can calculate the E0 cell. If you want to calculate the E0 cell also, here in this case, copper should be forming the anode and magnesium the cathode, isn't it? So the cathode will be E0, cathode is Mg2 plus bar Mg, and E0 Cu2 plus bar Cu. Let us see the values. It is minus 2.37 volt, minus 0.34 volt, which is negative. When E0 cell is negative, there is no cell setup and the reaction cannot take place. Hence, we can store. Yes, we can store. Hope it is clear to you. I am concluding the session with a question. Iron and nickel electrodes are used to form an electrochemical cell using a salt bridge and a voltmeter in the circuit. In which half cell is reduction taking place? Next question is, write the half cell reaction. Which is the anode? What are the carriers of current in the external and internal circuits? And then finally calculate the E0 cell. You think of the answers, work out, and then check with the solution which follows. hope you could match your answers with the solution given here. Thank you.